Hello students, how are you? I hope all of you are doing good. Welcome to another physics session. Today we will talk about geometrical optics. So let's get started with the definition of optics. Optics is a branch of physics that deals with the study of light. So it discusses the nature, behavior and interactions of light with matter. It explains how light travels or refracts through lenses, mirrors and other optical devices. Light behaves as a wave and also as a particle, which is called the wave-particle duality. Depending on this, there are three branches of optics: physical optics, geometrical optics and quantum optics. Physical optics discuss the wave nature of light. So it describes the phenomenon of interference, diffraction, polarization, like that. So this physical optics is called the wave optics also, because in case of physical optics, light is treated as a wave. On the other hand, in the case of the geometrical optics, light is treated as a particle. It explains the particle behavior of light. So it discusses the phenomenon of reflection, refraction. So we explain this reflection, refraction using the ray diagram, right? So we draw the light rays and then we explain this reflection and diffraction phenomenon through lenses and mirrors. So that's why this geometrical optics is also called ray optics. And in geometrical optics, the light is treated as a ray. Okay. The third one is the quantum optics. This is basically combined the wave-like and particle-like properties of light. Okay, so we will focus on geometrical optics today. So in this session, we will show how we get the image formation when a light passes through the lenses and mirrors. So if we want to define lens, you see here I defined lens briefly. So it is a transparent optical device bounded by two surfaces and at least one of which is curved. Okay. It refracts, bends light rays and can either converge or diverge them. Depending on this converging and diverging property, there are two types of lenses. One is converging or convex lens, another is diverging or concave lens. Here you see in this figure the converging lens. It is thicker at the center and thinner at the edges. As you can see, this red figure, and this is the shape of the converging lens, and it is also denoted by this way. And the refracted rays after passing through the lens and then meet at a point. We will talk about this later. So this is the structure shape of the diverging or concave lens. This is thinner at the center and thicker at edges. And this grid shape, this is the diverging lens. And in case of diverging lens, the refracted rays, they spread out. Okay, and we'll talk about this thing now. So I can show you the lens. So this is a converging lens. This is the shape, and this is a diverging lens. Okay, so we have these two lenses, and these lenses, they are made of glass or plastic. So these are glasses. Okay. Okay, so now we'll talk about the image formation in the case of these two lenses. So first, if we see the converging or convex lens, so you see this is a converging lens here, and so this dotted line, this is the principal axis of this lens, and this is the vertical axis. So we have the object in front of this lens. This is the object, and from this object, the ray of light, they are incident of this converging lens, and after so when the incident and then refracted through the lens. So after refraction, these rays they meet at this point, so they converge at this point. So that's why this is called converging lens. So since the refracted rays they meet at this point, so we get an image on this point, and this image is called the real image. Okay. So this is the height of the object, which is denoted by HO, and this is the size, height of the image, which is denoted by HI. And we see that the image is smaller than the object in size. So the size of the image, it depends on the position of the object. Okay. So we also see that this image, the object in the upward direction, but here the image in the downward direction. So this arrow, this is upward, here the arrow is downward. So that's why this image is called the inverted image. So inverted means the direction is opposite of the object. The image is formed below this principal axis. Okay. So in the case of the converging lens, we get a real and inverted image, and this is smaller, but it could be larger also compared to the object. It depends on the position of the object. So we have some parameters here. This is the DO, which is the distance from the object to the lens. This is DI, which is the distance from the lens to the image. And we have these 2 points here, the black points. This is called the focal point, and the distance from this point to the center of this lens is called the focal length, which is denoted by F. Okay, so this is the scenario. This is the image formation in the case of the converging lens, and we can see this is the observer, this image formation. So if we know all of these parameters, we can write this equation for the focal length, which is 1 over F is equal to 1 over DO plus 1 over DI. So if we know the distance DO and DI, then we can calculate the focal length. Also, if we know the focal length and any of the distance, say we know DO, then we can also calculate another distance, DI. So this is the relation between this among this focal length and these two distances. We have another expression also, which is called the magnification. Magnification is defined how much the image is bigger than the object. Okay, so this is denoted by this upper case m, which is equal to negative di over do. We can also write m is equal to si over so. So as I said, si is the height of the image, so is the height of the object. So if we know that, we can put here and we can easily calculate the magnification for this converging lens. This is the same expression for the diverging lens also. So there are two cases here. If m is less than 0, then we get real and inverted image. What we saw here in the case of the converging lens. But if m is greater than 0, then we get virtual and erect image. So this virtual and erect image formation, we can see that in the case of the diverging lens. So in this figure, you see this is a diverging lens, and this is this dotted line. This is the principal axis, this is the vertical axis, and here we have the object. Is O is the height. So from the object, these rays, so this way the incident on this diverging lens, and then they spread when they refracts from the diverging lens, they spread it out, right? So they do not meet at any point, like in the case of the converging lens. In the case of converging lens, after refraction, the refracted rays, they meet at this point. But in case of diverging lens, you see here they are spreading out the refracted rays. They do not meet at any point. So if we see, then we will actually observe this. That's why this is called diverging lens. The refracted rays, they are spreading out from the diverging lens. So, but if we extend these refracted rays like in the backward direction, then they meet at this point. This is the intersection of the extended refracted rays in the backward direction. Then it looks like these rays are coming out from this point. Since the refracted rays do not really meet at any point, so that's why we get the virtual image in this case. We only get the image if we extend the refracted rays in the backward direction, I mean behind the lens. So that's why this is called virtual image. And in this case, the object in the upward direction and also the image in the upward direction. You can see this arrow in the same direction, the object and the image, they are in the upward direction. So that's why this image is called the erect image. Erect means in the upward direction. The image is in the same direction of the object. And here also the image is smaller in size compared to the object. And we have the distance, like from the object to the lens is do, and the distance from the image to the lens is di. We also have the focal length from this focal point to the lens, which is denoted by f. And using all of these parameter, we can also write the same expression for the diverging lens. Also, we have the expression for the magnification. If we know the height of the image and height of the object, we can also calculate the magnification for the diverging lens. So that's the image formation. the ray diagram, and we explain this image formation in the case of the converging and diverging lens. In case of converging lens, we get the real and inverted image. In case of diverging lens, we get virtual and erect image. And another thing, you can notice that in case of converging lens, the object and image, they are on different two sides of the lens. But in case of diverging lens, the object and image, they are on the same side. So here image is formed behind the lens, and here image is formed in front of the diverging lens. So this is the basic discussion for the geometrical optics, and we explain the formation of image using two different types of lenses, converging and diverging. So we can also explain this image formation using mirrors. For this session, we talked about the theoretical concept of geometrical optics. In the next session, I will show you how we get this image using different types of lenses. I mean, converging, diverging. We can also combine converging and diverging lenses, and I will also use mirrors to show this image formation. So that's it for today. I hope see you in another session. Till then, take care, and thank you everybody.